Hello, welcome to the B&H engineering project titled Hope for Peru, which is about delivering water to a remote village in Peru. The problem is Catamarca does not have access to water. Its geography leads to droughts, the place has no infrastructure for water collection, and what little water there is often contaminated. The goal of the project is to make a water tower that can hold 200 gallons for 200 people for 2 days. We are partnering with a nonprofit organization called water.org. B&H Engineering is a Christian organization, and as Christians, we believe value and dignity for human life come from our Creator God, as it talks about in Genesis 1. We believe to live out the faith is to be imitators of Christ, who calls himself the waters of life. A verse that summarizes this conviction is from James, and it reads, "Religion that is pure and undefiled is to visit orphans and widows in their affliction." Orphans and widows is often used during the Old Testament to refer to vulnerable and forgotten people of Israel.
Thank you, Hunter, for that lovely presentation. So let's jump straight into the engineering part of our project. So as you can see, this is the first design that we came up with. I was the one mainly responsible for all of the designs, so this is what I drew. As you can see, it's very simple, very straightforward, as that was what I was aiming for. Little did I know this doesn't really work in SolidWorks because as you can see, the downward force that the tank exerts on the truss structure is not placed on a joint. And we just couldn't figure out a way to simulate this in SolidWorks. Additionally, the hand calculation for this truss was a lot more complicated than we expected it to be. So I proceeded to come up with two different and better truss designs. The first design, design A, was modeled after a common truss structure called the Warren truss. As you can see, this truss is essentially made up of several equilateral triangles. And this is the front view from SolidWorks. The second design, design B, was modeled after the Howell truss, which is also a very common design in the real world. As you can see, this is our design looking from side in SolidWorks. This is very similar to the previous design, and as you can see, the most noticeable difference is that two beams have been made vertical, so that now instead of having essentially a bunch of triangles stacked up together, now you have a square or a rectangle in the middle. But other than that, everything else pretty much remains constant. So those are the two designs that we came up with. We also did some simulations to figure out which design is superior, more reliable, and more stable so that we could implement the better one. But before going into the two simulations that we did, I thought it would be helpful to go through some initial parameters first. So as you can see on the left-hand side, again, the maximum capacity for the tank is 200 gallons of water, and together the water and the tank add up to about 3,300, give or take, pounds. As you can see, that is significantly larger than the wind force, and this manifests in results that I will be discussing in the next few slides. All right, so moving on to the results. So this first simulation that we did was the deflection simulation. So as you can see, both designs are relatively safe. These are very brief summary of what we got from our simulation. Neither of the two designs shows a deflection that is above 1 millimeter, which is assuring because, as you probably know, 1 millimeter is very inconsequential. So overall, we're very happy about this. Although you can sort of see that design B is slightly more deflected around the center of gravity compared to design A, but again, this is in the millimeters, so I'm not too concerned about it. It's also worth noting that the wind force almost had no impact on the deflection whatsoever, and that's sort of what I was mentioning on the previous slide, because when you're comparing the impact of 3,000 pounds versus 1 pound, the difference is paramount. Since the deflection simulation left us pretty much inconclusive with regard to which design was more safe and reliable, we had to do another simulation. So what we did was applying virtual loads to our two designs respectively again, and calculated the force experienced by each beam member. And the results were significant. As you can see, design B experienced way less variation in terms of the beam force compared to design A. So for example, at half capacity, so when the tank is half full, the beams in design A experience anywhere from 300 to 950 pounds, whereas that gap is much more shrinked in design B, so from around 600 to 950. Well, this is significant as it shows us that the load is more evenly distributed in design B, and we believe that this is a very important indicator of safety, as when you're designing a structure, you want all the members to be sharing the job, and you don't just want one member to be bearing a lot of the weight and some members to be essentially doing nothing. So all in all, we consider B to be the superior option. So after all of the hard work, we finally have a winner. Design B. So this picture right here sort of represents our thought process as we did this project. So first we came up with the design on the right hand side. It didn't cooperate with us as we were trying to do the simulation, so we proceeded to the other two designs, design A and B. Design A, the Warren truss, was safe in terms of deflection, but the force was a little unevenly distributed, so first place was reserved for the Howell truss, design B. So since B is the winner, we thought we would just include technical drawings for B here. So as you can see, two of the drawings are for the truss structure, and the remaining two are for the tank itself. And this is the top side view of the whole structure with the tank on top of the truss structure. So that is the end of our presentation. Thank you for bearing with us and watching. We hope you enjoy it, and we wish you have a wonderful rest of your day. Goodbye.